All right, today we're going to look at the different types of isomers. This will be a two-part series. Okay, we'll start off with what are called constitutional or skeletal isomers. And for the formula C5H12, there are three possible structures. Here is a model of pentane. The hydrogens are omitted for clarity. And if you look at the model, you can rotate it so it does, in fact, have this zigzag-like shape, but it's not fixed in that position. So this is pentane, sometimes called N-pentane for normal pentane. All right, here we have 2-methylbutane. We always want a number from the end that will give us the lowest possible number. So 3-methylbutane would not be correct. Butane is the longest chain since it's 4. And then the third isomer, commonly called neopentane. In the IUPAC, it is 2,2-dimethylpropane, and this is its structure. Okay, next we are going to look at what are called positional isomers. And for this, I'm going to assemble the different isomers for C4H9Br. Okay, there are 4 possible isomers. 2 are based on butane, a straight chain structure, and 2 are based on isobutane or 2-methylpropane. Okay, so the 2 possibilities, I'll use red to represent bromine. Okay, one possibility is this one. This is 1-bromobutane. I'll put the bromine here. Okay, bromine as a substituent is a bromo. So this is 1-bromobutane. Okay, and the other possibility would be to have 2-bromobutane. Okay, there is no 3-bromobutane because that would simply be a repeat of 2-bromobutane. Right, the other 2 isomers are based on isobutane. Okay, so here is isobutane. And we have 2 sets of hydrogens. We have these 9 primary hydrogens or methyl hydrogens, and then we have 1 here in the middle. So there's 2 possible mono-bromo compounds. There is this one. Okay, I could have substituted any one of the 9 with the bromine. Okay, and that would look like this. This is the this structure here. Commonly, that's called isobutyl bromide, but in the IUPAC, okay, the longest chain is 3, so that's propane. And we want to give our substituents the lowest set of numbers. So this would be position 1, position 2. So this would be 1 bromo, 2 methyl, propane. Okay, the other isomer we can get by placing bromine here. Here that would look like this. Bromine is in the middle. Again, our longest chain is propane. And this time it would be, instead of 1 bromo, 2 methyl, it would be 2 bromo, 2 methyl. Okay, so those are the 4 isomers of C4H9. Okay, note the overlap here between constitutional isomers and positional isomers. 1 bromobutane and 2 bromobutane, these would be considered positional isomers. The functional group is in a different position. These two would also be considered to be functional group, positional isomers. All right, the next type of isomer that we're going to look at are the functional group isomers. And for the functional group isomers, one example here is for the formula C2H6O. We have 2 possible structures. Okay, one is an alcohol, and I didn't spell that, let me correct that. Alcohol. The other one is an ether. Right, so here is a model of the alcohol. Okay, red represents oxygen in this case, and this is the alcohol hydrogen. These would represent lone pairs on the oxygen. We have 2 lone pairs on the oxygen. Okay, because of the tetrahedral geometry, this has a bent shape. Okay, this compound is ethyl alcohol, or as I like to call it, Ethel the dog. Okay, if I place an oxygen between 2 carbon atoms, this, okay, that's now an ether. Okay, we haven't learned how to name these functional, particular compounds from these functional groups yet, but this would be dimethyl ether. And again, we have 2 lone pairs on the oxygen. Okay, and this also helps to explain the bent shape. Okay, for the formula, C3H6O, okay, notice that the ratio here is 2n to 2, rather than 2n plus 2, 2n to n, rather than 2n plus 2 to 2. We've lost 2 hydrogens in forming our double bond. Okay, so these are some of the possible isomers for C3H6O. There is one more that I didn't show, but it's unstable and it would rearrange. I'll go ahead and show it. That looks like this. Okay, it's usually very unfavorable to have an alcohol group right on an alkene group. It'll just rearrange. I've got too many carbons there. Okay, then to make a bottle of this, right, what we do, okay, this is a CO double bond. This is the piece we use to designate a double bond. These are the lone pairs on the oxygen. And I'm going to zoom in just a little bit. These are the lone pairs on the oxygen. And if we have a hydrogen attached to one side of the carbonyl, then it's an aldehyde. Okay, we could also have a hydrogen attached to both sides, but that doesn't fit this formula. Okay, so this is okay, so this is an aldehyde. Okay, here's our CO double bond. Here's our aldehyde hydrogen, and okay, it's got 3 carbons. Okay, now to make this a ketone, okay, I would remove this hydrogen, and I need to place the carbon on this end. All right, so here I have the carbonyl, the CO double bond, between 2 carbons. That's now a ketone. Okay, and this is a familiar compound, acetone. Okay, and then there's a couple of other possibilities here. This one has an alkene and an alcohol. This one has an alkene and an ether. And this one is not stable. It's going to rearrange. It's actually going to rearrange into the aldehyde. All right, next we're going to look at stereoisomers. And those are configurational isomers that we've looked at so far. We changed the configuration, we changed the skeleton, we changed the position of the substituents. Now we're going to look at what are called stereoisomers. And for stereoisomers, we have configurational and conformational isomers that are possible. Okay, we're going to start off by looking at conformational isomers. Okay, here I have ethane. So these represent carbon atoms, and this would be what we call the staggered form of ethane. Okay, where this hydrogen is up, this one is down. This bond, and this bond are all in the plane of the board. All right, we've got one hydrogen back, one forward, in the same way here. This is what's called a sawhorse projection. And this is the staggered form of ethane. Okay, one thing to be aware of, and that is that a dash and a wedge always have to be on the same side of 2 solid lines. Okay, so this is correct, but it would not be correct to show something like this. dash and the wedge always have to be on the same side of two solid lines. Okay, also, we cannot have two dashes or two wedges on the same carbon. Okay, this is also incorrect. And as you'll see from the model, this is actually impossible. Okay, if we have this hydrogen in the plane of the board, it's not possible for both these hydrogens to be coming forward. One has to come forward, one has to go back. Okay, so these are both incorrect representations. Right, that's the staggered. And then the other major conformation is what we call the eclipsed. Okay, so this is the eclipsed. These are sawhorse projections, and then to show the Newman projections, right? What we do, we'll take this and rotate it like this. Draw a circle. The carbon in front have the substituents originate from the center of the circle. The carbon in back, these will originate from the outside of the circle. So that's a staggered, this is the eclipsed. We do rotation where our CH bonds are all lined up. So that's staggered and eclipsed. Right, for butane, again, we can draw sawhorse and Newman projections for butane. Okay, so here I have butane. And we'll start with what we call the fully eclipsed. And I replace two of the hydrogens with CH3s relative to ethane. Okay, so I have hydrogen coming forward, one going back. Okay, so this would be fully eclipsed. Okay, and this is the highest energy, the least stable form of butane. Right, the most stable form is what we call anti. Anti. Okay, the methyls are 180 degrees apart from each other. You know, to make the Newman projection, we do the same thing that we did with ethane. We'll sight along the bond between carbons 2 and 3. We'll do a 90-degree rotation like this. We'll draw a circle. And that would be the fully eclipsed. Anti look like this. Okay, the anti is the lowest energy, most stable. And I'm going to show you two more here. One of these this one is just called eclipsed. Fully eclipsed is where the two methyl groups are lined up. And then the fourth one is called gauche, G-A-U-C-H-E, gauche. Okay, here the angle between these two methyls is 60 degrees. Okay, there are multiple gauche conformations. Okay, next we're going to look at cyclohexane chairs. And the first one I'm going to show you is 1,3-dimethyl cyclohexane. We're still talking about conformations. So to draw a chair, to offset parallel lines. I draw the axial in first, so down, up, down, up, down, up, and then the equatorial. This one will be parallel to this bond right here. This one will be parallel to this bond. Three on the right point to the right, three on the left point to the left. So this one will be parallel to the second one over. This one will be parallel to this one, and this one will be parallel to this bond right here. So those are axial and equatorial. And we'll start off with the cis 1,3-dimethyl. Okay, so I have my cyclohexane chair. And, okay, so I'll put this methyl on top, and And I'll also put this methyl on top. Okay, so cis. Dimethyl. Hexane. Okay, I can start anywhere. I'll start here. Okay, so that's 1, 2, 3. Okay, so that's the cis. And that would look like this. This is the cis 1,3-dimethyl. Okay, when I do a conformational change, that is, I take this carbon that's up, I bring it down, and I bring this other one that was down, I bring it up. Okay, notice what that does. That puts both of these methyls into the equatorial position. Okay, still cis 1,3-dimethyl because I haven't broken or reformed any bonds. Okay, when both of these substituents are axial like this, you have a lot of steric strain. There's 1,3 diaxial interactions where these methyls bump into each other and they repel each other. All right, so that means that this form is more stable, lower energy. Okay, next we'll compare the trans. One, 3-dimethyl cyclohexane. All right, so to make the trans, okay, I've got the cis right here. And so what I need to do is I'll take one of these, remove it, and put it on the other position, like that. Okay, so for the trans, I'm going to have one axial and one equatorial. Okay, when I do the conformational ring change, right, the group that was equatorial becomes axial. The one that was axial now becomes equatorial. Right, so these would have the same energy. They would have equal energy. Right, the other two that we're going to look at are the cis and trans 1,4-dimethyl. We'll start off with the cis 1,4. and arbitrarily place this one axial. Okay, so we'll have a hydrogen here that is equatorial. Okay, so 1, 2, 3, 4. Okay, so we'll have an axial and I'll have an equatorial. And for this to be cis, methyl needs to be on the bottom. Okay. So this is cis 1,4-dimethyl. And we have one axial, one equatorial methyl. Okay, when I do the conformational change, okay, this methyl is now axial, the other one is equatorial. So actually, let's make this 1,4. Okay, it's still methyl because the methyls are on the top, hydrogens are on the bottom. Okay, so this is now axial, and this one is equatorial. Okay, these would have the same energy. Okay, so that's a cis. All right, let's look at the trans next. Right, so this is the trans 1,4. And in this conformation, both of the methyls are axial. Right, so to make trans from the cis, we've got to break and reform a bond. Like this. Okay, here they're both axial. There's some steric interaction between this methyl and the hydrogens on the third position. So that makes this one less stable. Okay, if we do the ring flip, these now both become equatorial. Okay, it's still trans because I haven't broken or reformed any bonds. If you compare the hydrogens, I think it's clear, it's more evident that this is the trans isomer. Okay, in this case, these are not the same energy. This one would be lower energy. Okay, notice that there's a change when we go from the 1,3 to the 1,4. With the 1,3, the cis isomers, the cis isomer conformations were not equivalent. One was diaxial, one was diequatorial. The trans isomer of the 1,3 had two conformers that were equivalent. But with the 1,4, it's different. With the cis, this time, the two conformers are equivalent, but with the trans, they're not. All right, next we're going to look at stereoisomers. And the first type of stereoisomer that we're going to look at are what we call geometric isomers. And there's two possible ways that we can have geometric isomers. One way would be if we had a carbon-carbon double bond. All right, so here I have a double bond between the two carbons. I do not have free rotation like I did with the butane. Since this is a chain that consists of 4 carbons, instead of butane, it's now butene. But we do need to specify where the double bond is located. Okay, this is the newer method, okay, where we say butene. You'll see this a lot in the literature. Some textbooks even still refer to it as 2-butene. All right, there are 2 geometric isomers for 2-butene. This one is the cis. Go to the trans isomer. Go to the trans isomer. I'm going to have to break a bond and reform it. Okay, these are what are referred to as stereoisomers because they're a type of stereoisomer called cis-trans or geometric because the carbon skeleton is the same, the position of the functional groups is the same, it's between 2 and 3, but the 3-dimensional shape is different. All right, next we're going to look at 1-bromo, 1-chloro, 1-propene. Okay, propane is 3 carbons. Double bond actually has to be between 1 and 2. So 1-bromo, 1-chloro, 1-propene, and I'm going to use green to represent chlorine and red to represent bromine. Bromine is a red-brown liquid. Chlorine is kind of a greenish-yellow gas. Right, so this is 1-chloro, 1-bromo. Actually, I have switch that around here. Okay, so the methyl's on top, bromine's on top. This. Okay, if I have this isomer, okay, these are clearly different. Okay, I cannot line up all of the groups at the same time. In order to convert this one to this one, I actually have to break this bond and break this bond and switch these two. Okay, so these are different isomers. Okay, as far as cis and trans, okay, this is where we run into difficulty. These are clearly different, but which one is cis and which one is trans? Okay, so for this reason, there was developed a system called the E and Z method. Okay, this is actually more precise than the designations of cis and trans. It can apply to compounds such as this. We can also apply it to the previous structures that we just had, cis and trans 2-butene. We can assign an E and a Z configuration. All right, these come from two German words. This is Gagen. That correctly. And then this is zusammen. This is opposite. This means opposite in English. And this means together. All right, so what we do is we compare the two substituents that are on each carbon of the double bond. We compare them separately. And we assign priorities based on atomic number. All right, on this side, look at the periodic table. Carbon is number 6, atomic number 6. Hydrogen, of course, is atomic number 1. So hydrogen is a lower priority. Okay, over here, chlorine is atomic number 17. Bromine is 35. So bromine has the higher priority based on atomic number. Okay, priorities are the same. Okay, carbon is higher than hydrogen. Bromine is higher than chlorine. Okay. Then we compare the two higher priority groups. Okay, and since these are on Z same side, this is the Z. And here the two higher priority groups are opposite, so this is the E. Okay, we would put the configuration letter in front of the name. So this is, first one is Z in parentheses, 1 bromo, 1 chloro, propene. You could say 1 propene, but with 3 carbons, there's only one place we can put a double bond. And then this would be E. 1 bromo, 1 chloro, propene. Okay, it's propene because it has a double bond. Okay, there's a couple more aspects to the E and Z that I want to show you. Okay, for example, if I have something like this, if I were to switch these two groups or switch these two groups, but not both, I would have a different isomer. Okay, in order to determine E and Z, again, we compare atomic numbers. We compare the atomic number of the first atom. Okay, well, that's easy in this case because carbon wins out over hydrogen. Okay, here we have carbon. Those are the same, but these are two different groups. Okay, so we compare the second atom, and it is carbon versus oxygen. Carbon's atomic number 6, oxygen is number 8. Okay, so this group wins out. Okay, so this would be the E isomer. Okay, as soon as we find a difference, we stop. If we have a double or triple bond, in a situation like this, let's compare this side first. Okay, here we have carbon. Carbon is the first atom. Okay, we work our way out to the next one. The next one out would be a hydrogen for the methyl. Next one out is a carbon. So ethyl beats methyl. Okay, on this side, carbon is the same. Carbon is the same. And for the double bond, we treat this as though it's 2 oxygens. And so 2 oxygens and a hydrogen would beat 2 hydrogens and 1 oxygen. Okay, so this one would have a higher priority. And so this would be the Z isomer. If we have, say, something like a CN triple bond, okay, we would count that as though our carbon was bonded to 3 nitrogens. Okay, and then finally for this part, I'm going to make a model of 1,2-dibromocyclopentane. Right, so I will use bromine as these red spheres. Okay, so this would be 1,2-dibromocyclopentane. And this is the cis isomer. Okay, and there's a couple of different ways we could represent that. So this is the cis. Cyclopentane. One way we could represent that is like this. Okay, and it's also preferred practice to show the hydrogens or if there are other groups present on that particular carbon, those particular carbons. So that is the cis. Another way to represent that would be to draw it like this. And we could show both bromines coming forward or back, and the hydrogens moving back. Go from cis to trans. Okay, I'm going to have to break this bond and then reform it on the bottom like that. Right, so the trans we could represent like this. Or we could show the ring in the plane of the board. This one coming forward. This one going back. So those are two ways we could represent the trans. Okay, in the second part of this lesson, I'm going to talk about what are called optical isomers. And I'm going to go ahead and end this meeting.